Hello everyone, we are discussing linear algebra for our data analysis course, and in this lecture I will discuss about system of linear equations and how to solve them. So, let me start with a data set which is very popular among the people who learn machine learning and data analysis. This is called iris data set, and it has been collected by one botanist and has been used by a famous statistician Fisher in his old paper, I think in 1936 or something, for some statistical work. And it has the data for the size of the morphological properties of certain iris flowers. And what I have done, it is a large data set. From that I have picked up a particular part and I have plotted the data here. You can see the diagram. So, I have sepal length in the horizontal axis and petal length in the vertical axis. Just look at the data. Looking at the data, you can easily see there is a linear trend, is not it? There is a linear trend between the sepal length and the petal length. So, your obvious tendency would be to why do not I fit a straight line to that, and you must have done that this type of exercise many a time using even Excel sheet you may have done fitting a trend line which is a linear one. And I have just done that, and in our technical jargon we will call it I have done a linear regression. We will learn linear regression in a later on. So, what I have got a relation between sepal length and petal length, and that is written here. Petal length is equal to 0.75 into sepal length plus a constant term. So, this is typical of a linear equation, is not it? In our school we have learned about the equation of a straight line, which is a linear equation, y equal to mx plus c. I have two variables y and x, and m and c are constants. Similarly, there is nothing specific that I have to keep only two variables y and x. I can have multiple variables, but I can still have a linear relation. For example, I can have something like this: y equal to m1 x1 plus m2 x2 plus m3 x3 and a constant. This one is also linear because you look at it, the power of these x and y's is 1, right, and there is no multiplication between these terms, this variable. So, this is a linear equation representing linear relation between these variable 3 x's and 1 y, whereas m1, m2, m3 and c are constants. Usually in our data analysis and linear algebra, we do not write this equation in this way. This is the way you usually write when you do coordinate geometry in school, right. What we do, we write the same thing in this fashion: a1 x1 plus a2 x2, a3 x3, a4 x4 equal to b, where x1, x2, x3 and x4 are my variable. You can simply replace this y by x4 and then rearrange the m and c term, you will get back this one: a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 equal to b. And this is a linear equation because all this variable has power 1 and there is no fancy function, right, like sine, exponential or something like that, or there is no product between these variables. So, this is a linear equation. Now, this is only one linear equation, but in our data analysis usually we will have multiple linear equations. So, what do I get? I get a system of linear equation, and I have shown an example here. So, I have two equations here. So, this is a system of two linear equations: a11 x1 plus a21 x1 equal to b1 and a12 x1 plus a22 x2 equal to b2. Notice that in both the equation I have x1 and x2. This a11, a22, these are the constant and they can be any value, right, negative, positive, 0, whatever it is. Similarly, b and b1 and b2 also. I can have a system of equations involving 3 variables. For example, I have shown here 3 variable based system of equation. I have 3 variable x1, x2, x3, and I have written 3 equation. I have a purpose for writing 3 equation. I could have written 5 equation also. It does not matter. But as a whole, I have multiple equations involving this variable. That is why it is called a system of linear equations, right. All of them are linear. So, it is a system of linear equation. Now, let me move from this system of equation to matrix based or vector based representation of a system of linear equation. How do I do that? Let me take a 2 equation 2 variable system. I have 2 variable x1 and x2, and I have two equations. Take the first constants which are multiplied with x1 and take the second one. Convert this one in one vector, suppose v, and make this one another vector, right. So, I take these constants or parameters associated with each of these variable, right, together, and I create vector. So, how I have done, what do I get out of it? I get something like that. So, now I can multiply this first vector a11 a12 with x1, then I will get back the same thing, plus I multiply x2 with the second vector that I have created. So, I will get back these terms, and the constant on the right hand side I represent also as a column vector b1 b2. Now, using the rules of matrix multiplication, you can easily represent this relationship as this format. So, what I have a matrix here which has these vectors arranged side by side as column vectors of that matrix, and then I multiply that with a vector made of my variables. So, this is a variable vectors, and obviously, I have the right hand side constant as a separate column vector. Just try to remember the rules of multiplication. What I have to do? I have to take this row and multiply with this one. So, then I will get back this part of the first equation, a11 into x1 plus a21 into x2. Now, take the second row of this matrix and multiply with the same vector x1 x2. What will happen? You will get the second equation's left hand side, a12 x1 plus a22 x2. So, that means a system of linear equation is given to me. I can represent it as a compact form using a matrix and few vectors. So, as a whole, I have written it down in a shortened form. So, this is the given equation for me, and I can represent that as a matrix into a vector in is equal to another vector. So, this first matrix is called A, and it is called the coefficient matrix, whereas this one is called the x vector, which is the variable vector, and this one is my constant vector. So, what I have got? I have got A into x equal to b. This is the shorthand form of writing a system of linear equations. So, A has all the constants. So, it is called coefficient matrix. So, I have a coefficient matrix into the vector for variable. Here in case of the variable are x1 and x2, this multiplication product is equal to the vector on the right hand side, which is b. So, Ax equal to b. Now, I can do the same thing if I have 3 equations. So, I have 3 equations here for 3 variables. So, I will take the constant term which are marked in yellow, you can see easily, and I will create the coefficient matrix A, whereas the variable vector, the column vector will be x1, x2, x3 stacked one over each, and on the right hand side of the equal to sign I will have the vector representing the right hand side term of my original linear equations. So, again I will get back Ax equal to b. So, this is the shorthand form of writing a system of linear equation. Now, when we are writing this one, you must have noticed one thing, the rule of multiplication must be satisfied. So, what is the dimension of this one? This is 3 into 3, right? I have 3 rows and 3 columns. What is the next vector? Vector is 3 into 1, because I have 3 rows. So, obviously, this is equal to this one. So, I can do the multiplication, and the resultant will be 3 into 1 vector, and I have 3 into 1 vector here. So, the rule of multiplication is satisfied. So, usually this m here I have 3 equation. So, number of equation is represented by m. It is not mandatory that you have to call it m. For our discussion, we will call the number of equation equal to m, and the number of variable in this case is 3, that is n. So, the coefficient matrix is m into n matrix, whereas the variable vector is n into 1 vector and the constant vector on the right hand side is m into 1 vector. This way of numbering and naming the number of equation and number of variables is important, because I will enter into a discussion where we will see the effect of m and n on our calculations, right. So, we have got a shorthand representation, or rather a linear algebra based representation of a system of linear equation. But why I am taking so much of trouble of that? Because many a time we will use linear algebra to solve a system of linear equations. What do I mean by solve a system of linear equation? We will have some data, right, and that data may be represented by this matrix and this vector, and I want to know the value of x1, x2 and x3. So, in my problem, in my data analysis, the coefficient matrix and the constant vector, these may be coming from some equation or from data, experimental data, whereas the variable x1, x2, x3 will be unknown to me. So, I have to calculate these unknown variables, right. So, that is why when we are solving linear equations, we call these variables unknown. So, we have to solve this system of equation, and linear algebra helps us immensely to solve large system of linear equations, and most of the solver in your computer will use linear algebra to solve it. So, let us take a small system and try to solve that one using first general method and eventually using linear algebra based method. So, I will take an example, very simple. X plus y is equal to 2, x minus y equal to 0. I can represent it as a coefficient matrix, in linear algebra term. I have 1 here, 1 here, 1 here, 1 here. So, my A, this is my A will be 1, 1, 1 minus 1, and this is my x vector, and this is my B vector 0 and 2, this is right. The number of equation is m, number of variable is 2. How will you solve it? Very easy to solve, every one of us has learned that in school. So, what I will do, I will take this second equation, and from that I will get what? I will get x minus y equal to 0, that means y equal to x. Now, take the first equation and put that x plus y equal to 2, that means I will replace x y. So, this will be x, y is replaced by x, as I have done got from the second equation, that is 2. So, that means x equal to 1. So, that will give me y equal to 1 also. So, 1 1 is the solution, as simple as that. You do not need linear algebra or a computer to do that, right. But let us look into the geometric meaning of this solution. So, what I have done, this is the first equation, this is the second equation. In this 2D space, I have drawn those two. Those are straight line, right? The linear equation, that means they are straight line, and they are intersecting at this red dot. That is the solution, because at that red dot, the value of x and y satisfies both the line, straight line. So, that is my solution. So, for any linear system of equations, the intersection of these lines in my space will be the solution, right. So, we will try to use this concept to explore some system of linear equation. All of them are simple, but they will have different behavior. Let us take the first one, x plus y equal to 2, x plus y equal to 3. Just try to solve it. The second equation will give me x plus y equal to 3, that means y equal to 3 minus x. Then I take that and put in the first equation. First equation is x plus y equal to 2. I will replace y, x plus 3 minus x from here, from the second solution, right, second equation. So, that is equal to 2, x and x get cancelled, I get 3 equal to 2, absurd. This can't be possible, you are getting an absurd answer. Why is it so? Let us plot the graph and it will be clear why it is so. These are the two equations. and I have the two plots. This is possibly one and this is the second one. You can see these two lines are parallel. These two straight lines are parallel to each other. So, they do not intersect. So, there is actually no solution to this. In fact, this system of equation is called an inconsistent system, because if you notice the equation, this one, the first one can be multiplied with 1 to get the same on the left hand side. But on the right hand side, if I multiply 1, I do not get the same thing. That means, there is an inconsistency on the left hand side and the right hand side of these two equations, right. So, that is why it is called a inconsistent system and it does not have any solution. That means, all linear system of equations will not have solution. We have just started to explore those. Now, let me take another example. Now, I have increased the number of equations. So, my m is 3, number of equation is 3, but how many variables are there? 2, x and y. So, n equal to 2, that means, my m is greater than n. Number of equation is more than number of variable or number of unknowns, right. So, I have more equation than unknown. So, this system is called overdetermined system. I am not going to try to solve this equation manually. What I will do, I will graphically represent this system, 3 linear 3 lines, right. So, this is what we get. We have 3 equations and they does not all these lines do not intersect at one single point. What they have? They have 3 intersections, and none of these 3 is common to all of these 3. That means, this system has no unique solution, right. So, usually overdetermined system in general will not have any solution. As I said, in overdetermined system, my number of equations will be more than number of variable or unknown, and they will not have any solution, as I am showing in this example. So, you will be tending to avoid them, right, in your data analysis. But unfortunately, for most of the cases in data analysis, we will very frequently encounter this type of overdetermined system, where the size of your data will be much bigger than the number of variables. So, your A matrix will be a rectangular one, a tall and skinny one. So, is there a way to handle this? Yes. We will not be able to find a unique solution, as I explained using this diagram, but we can use some optimization technique to find a optimum solution, and that is what done in case of linear regression, that we will learn later in this course. We try to find out a optimum solution for this overdetermined system, as it does not have a unique solution. Now, let me give example of another overdetermined system. Here also 3 equation, 2 unknown, x and y. Let us plot the line. Now, in this case 3 equations are intersecting at one unique point. That means, I have a unique solution. How can that be possible? Just now few seconds back I said, if I have a overdetermined system where number of equation is more than number of unknown or variable, we will not have solution, and I have shown an example. Then how come this is happening? Where we are going wrong? Just pay attention to the equation and you really realize where is the problem. See, if I take this first equation, let me mark them 1, 2 and 3. So, I take the first equation, x plus y equal to 2, and then I multiply the second equation with 2. I get 2x minus 2y equal to 0, and I subtract this whole thing from the first one. So, what do I get? X minus 2x is minus x, y plus 2y, it will be plus 3y, and 2 minus 0 is 2. I have got the third equation. That means, the third equation is not independent. I can represent it by combining linearly the equation 1 and 2. That means, these 3 equations are not linearly independent. So, I can actually simply remove this third equation, and I will get back to a situation where I have 2 equation and 2 variable, and I have a unique solution. So, in this case it is over determined, but as the equation are not linearly independent, we can reduce the system and we have the solution. Now, let me move to the opposite side. We have over determined, now I will move to underdetermined system. What is that? I have given you a simple one equation, x plus y equal to 2. That means, number of equation m is less than number of variable n equal to 2. What will be the solution of that? You can easily guess that any value of x and y possibly will solve this, right? And in fact, that is true, any value. I have an infinite solution. I have drawn the diagram. This is my equation, right? This is x plus y equal to 2. Any point on this line will satisfy my equation. That means, for a underdetermined system where the number of equation is less than unknown or the number of variable, the system is underdetermined and have infinite solution. Just like overdetermined system, I do not have any unique solution here at all. Rather, I have an infinite solution, all of them are solution, and that is not useful for us. So, but unfortunately, in many data analysis cases you will encounter this, although you may not discuss this one in our course. What people do in that case, they again use some sort of optimization where they put some extra constraint on what is the possible value of x and what is the possible value of y, so that they can actually zoom into a particular region of this and find the optimal solution. So, what I have discussed till now is that if I have a linear system of equation, if it is overdetermined, I do not have a solution. Rather, we usually use optimization based method to find the optimum solution. Whereas, is underdetermined, I have infinite number of solution, again that is not very useful. So, the useful thing is when m is equal to n, and let us see how linear algebra can be used when m equal to n, number of equation is equal to a number of variables, how we solve it. So, again I will represent the whole system of equation as in a matrix notation, A x equal to b, A is the coefficient matrix, x is the variable vector, b is the constant vector. Now, I want to know x, right? This is my unknown. This is my unknown. So, I want to know x. Won't it be nice if I can simply take a on this side and divide b by a, I will be left with x on the left hand side. I am separating, right? If I can do that. But unfortunately, I cannot do division by a matrix, right? I cannot divide a vector by a matrix. So, what I will do? I will take help of matrix inversion. I will multiply both sides with A inverse. So, what I will get? I will get A inverse into A into x equal to A inverse B. Both sides of the equation I have multiplied with A inverse. Now, I know A inverse A by definition, and if you do any calculation will be in identity matrix, right. So, what do I get? I get I x equal to A inverse B. Now, I into x, identity matrix into a vector will give the same vector, because identity matrix is nothing but equivalent to scalar 1. So, that means I will get x equal to A inverse B, and that is what I want to do, right. Now, here is a catch. When can you do the inversion? Inversion of a matrix, if you remember the lecture on determinant and inversion of matrix, I can invert a square matrix only when it is of full rank. That means, if it is determinant is not equal to 0, and full rank of a matrix means its rows and columns are linearly independent. Now, think back where I am getting the coefficient matrix from. I am getting the coefficient matrix from the system of linear equations. That means, to have a full rank coefficient matrix, my system of equations, all those equations should be linearly independent to each other. If they are not linearly independent, I cannot do this inversion, determinant will be equal to 0 and I will not be able to get a unique solution. So, let us first see an example. I have taken a simple system, that the first one I started with, x plus y equal to 2, x minus y equal to 0. I have written it in the form of matrix, the coefficient matrix and the vectors. So, now I calculate the determinant is minus 2 and that is not equal to 0. That means, I can do the inversion of my coefficient matrix, and that inversion I have done using an online tool. You can also use them, right. So, I got the inversion. So, now I will multiply this A invert with B to get the x vector. So, that is what I have done, x equal to A inverse B, and this is a simple matrix multiplication that will give me 1 1, and in fact, we have done simple algebra to get that earlier. So, it is matching. So, now let me jot down what we have learned in this lecture. In this lecture, we have tried to understand the solution of a linear system of equations. So, first we started with what is a linear system, right, and then we have learned how to represent a system of linear equation in terms of linear algebra using matrix and vector as A x equal to b, where A is the coefficient matrix of m into n dimension, m is the number of equations, n is the number of variable or unknown, whereas x is the variable vector having n into 1 size, n is the number of variable. And then we have learned that if the determinant of A is not equal to 0 and A is a square matrix, that means the number of equation is equal to number of variable, and as the determinant is not equal to 0, A is a full rank matrix, then the solution, unique solution to x is x equal to A inverse B. Along with this, we have also learned about overdetermined system and underdetermined system. In overdetermined system, number of equation is much more than the number of variables or unknown, whereas in case underdetermined, this is the opposite. In overdetermined system, I have no solutions. Usually, we encounter them very frequently in data analysis, and in that case, we use technique like regression to find the optimum solution, but that is not a unique solution. An underdetermined system, m is less than n and it has infinite solution. It is actually not much useful for us. So, that is all for this lecture. Before I leave, I will give a problem for you to solve, a simple one. So, I have given here 1, 2 and 3 equations, all are linear. So, you have to solve this system of equation. You can easily use the algebra and replace values and do that like you have done in your school math, but I insist that you use the concept of linear algebra that we have learned in this lecture and solve it, right. So, for that you have to calculate determinant, you have to calculate invert of a matrix, all these things, and there, as I said, there are online tools available, search them out and use them and solve it, this system of equation using the concept of linear algebra that we have learned in this lecture. I am sure you will try it, then see you in the next lecture. Till then, happy learning.